Thanks for having us here. It's my pleasure to introduce Alex Smola. He doesn't really require much introduction. I guess I could introduce him by way of, from the perspective of someone entering the field only in the last 4 years. So previously I was a musician, and so I entered the field and I kind of encountered names through papers first and didn't have a face to put to them until recently. And so I mainly interacted with Alex through Google Scholar. And so I believed firmly that he was about 90 years old because of his H-index and citation count. So it was kind of nice to find out that we're actually quite comparatively closer in age. I've had the pleasure of working with him for much of the last year, spending my final year of PhD at Amazon AI, where he's the director of machine learning. I believe still currently faculty at Carnegie Mellon. Yeah, I don't think he requires much more. So for Alex.
Okay. So thanks for the kind words. And so the first thing is a bit of logistics. I guess I already mentioned it before. We'll be finishing in line with the afternoon coffee break, simply because there's a deep learning session going on at 4 p.m. and I'm fairly sure all of us want to see the talks there. So this is really trying to get you started with deep learning, even if you haven't really done much deep learning at all yet, helping you get MXNet, get everything installed, get everything up and running, and getting you to the point where you can run parallel distributed jobs on multiple GPUs, multiple machines on AWS, for instance. And this is very much a tutorial to follow along. So we'll show you a couple of GitHub pointers and other places how to get started. This should help you follow along at least. I hope you have Jupyter and similar things set up. If not, we'll help you. So the first few minutes are probably going to be spent on just helping everybody get up to speed. Before going into a lot of details, let me quickly go a little bit over. I mean, you may have heard of MXNet. You may not have heard about MXNet gluon, and so I should probably explain a little bit what this is all about. It's a fairly new API, and for that, let's start with something very primitive, namely basics of how to write computer code. And so there's the first thing, obviously, you can write the program in a declarative way. I mean, that's kind of a slightly weird way for most computer scientists. You define a variable, you define another variable. You decide how they are supposed to be combined. You build essentially the equivalent of a compute graph, and then you say, now compile it, and then you execute it. Well, you might think this is weird. Mind you, this is actually how a lot of deep learning frameworks work. So for instance, in TensorFlow, you build a compute graph. In Keras, you build a compute graph. This is pretty much the standard way of how you build a lot of deep networks. And there's obvious optimization opportunities. It's very easy to serialize the network, do a lot of those things. But it's kind of a pain sometimes if you want to debug it, because you never know where exactly things go wrong. Now, the alternative, and this is how we pretty much all grew up learning how to code, at least most of us, I think, unless we come from the declarative land, is imperative programs, where you basically say, well, A is some vector, B is another vector, maybe multiplied by 2, and then C is the product of those two vectors. Then print out that variable, and printing out that variable allows you to, for instance, analyze, debug, and everything, right? This is basically exactly what you can use for standard debugging, and this is great to write things, and it also gives you good potential to have nice dynamic structures. So for instance, you can have something that goes through an entire parse tree, and if the sentence is longer, it might branch off in more pieces, and if it's shorter, well, it won't. The problem is usually that this is very hard to optimize for any deep learning framework, right? Because essentially every time you encounter something, it could be a new network, and the problem is, since every time it could be a new network, even if it's the same network over and over, you have to reparse it all the time. And that is very inefficient. So this is pretty hard to optimize. This can actually be fixed, and so one of the things why this is quite exciting, what I hope to be telling you today is that you can actually fix this with a just-in-time compiler by saying, hey, by the way, this piece of code, even though I programmatically defined it, well, shall remain frozen for the next coming time, and then you don't need to reparse it, and you get corresponding speed benefits. So let me just quickly situate all of that into a slightly bigger landscape. So gluon builds on MXNet, builds on all the backend, all the execution, the serialization, the graphs, the multiple language bindings, the parallelization, all the things there. However, it's a front end that borrows quite heavily from Chaina and then, by proxy also from PyTorch, because really there should be another arrow going from Chaina to PyTorch, which is pretty much the same API, and gluon is pretty close to that as well. So this is a little bit giving you at least some context as to why I think this is pretty nice, because it's very user-friendly. And so what I'll first do is we'll first actually walk you a little bit through the installation, and well, Zach and I will probably help you on your laptops getting everything up and running, just in case. And you might want to take some pictures of the slides when I put them up in, where all the pointers and installation commands are. So this way I don't have to keep those slides up for 10, 15 minutes, right? So who has used any deep learning framework before? Wow, that's actually quite a bit. Who's got Jupyter installed on his notebook? Okay, awesome. That's a bigger hurdle. Great. I suppose everybody here is running Python 3, right? Sort of, kind of.
Reluctantly.
I mean, the notebooks are set up for Python 3. You can, otherwise you'll have to change the print statements. Yeah, we were sometimes too lazy to import from future print with an argument, right? But who's installed MXNet before? Oh, wow. Okay, it's quite a few. Bad news for you, you'll need to install the latest version with ---- pre, because you may not have the latest release. So this is what we'll cover today. And so we'll start really gently by, just some background about deep learning. And given that a lot of you are experienced deep learners, some of that can probably be faster than other things. We'll make extensive use of notebooks, so I'll walk you through them. And my guess is if you're sitting in the back rows, you definitely want to clone the notebooks and walk through them on your own laptop, or move up to the front, because it's going to be otherwise probably a little bit harder to read. In any case, so after just, a basic intro to, how to get this all installed and, deep learning, just such that we have common shared terminology when we refer to things, we'll start with, the basic matrix format. It's called ND array and automatic differentiation and all of that. The next part then will be how to actually build neural networks in MXNet, both from scratch and then using gluon. And we'll talk about, MLPs, loss functions, convnets, and a bit of optimization and capacity control. Then we'll get to the slightly more fun topics, so generative adversarial networks. And they are kind of interesting because now you have an intricate, optimization loop, which is why, for instance, a lot of people like to code those things up in imperative languages. Then we'll talk about LSTMs, tree LSTMs, and then in the end, we'll touch upon scaling learning, so how to basically operate with the AWS infrastructure, how to design a parallel distributed optimization algorithm, and how to use it actually then, for instance, using the key value store and all the pieces in there. Okay, so now here's the most important slide. Right, take a picture of this. So if you have everything installed, CUDA on your laptop or whatever, right? You can just do a pip install, and that should work for Macs and Linux, right? You can also build it from scratch, right? So be aware of the fact that you need to git clone all the submodules, because MXNet relies on a whole bunch of other repositories like NNVM and parameter servers, and so on. And so make sure you initialize the submodules, right?
You don't need CUDA if you're running on your laptop. So if you're running on your laptop and you want to build without GPU, just use the final line there.
Yeah.
Just commented out to show you that you wouldn't run both the final and second to final line.
Yeah. So unless you have a really nice laptop with a GPU in it, and you're sitting close to a power supply, which you probably then have to, right? Then probably for the purpose of this, you can just, use the pip install MXNet and -- pre. That's really important because that's basically because it's a pre-release. And MXNet _ CUDA 80 requires that you have CUDA 8.0 installed. So it will not work on CUDA 7.5. I mean, you can build it for CUDA 7.5, that's not a problem, but if you want to do a pip install, there is no CUDA 75 build right now. It's only a CUDA 80 build. Okay, so with the exception of those, you already have, pip and everything set up, or those who have, CUDA 8 set up. Who doesn't fall into this category? Whose use cases are currently not covered by what I described? Hands up, please. Okay, so the question is, who is not taken care of by what I'm just describing? Okay, what's your concern?
It's just says permission denied. Hang on a second. Permanently added.
The HTTPS clone URL. That's the SSH clone URL.
Yes. So if you don't have. Okay. So by the way, just to make it clear, this is the easy and quick install. You don't need to do that if you can do this, right? So in other words, if you're on a Mac or on a Linux box with CUDA set up, do this. Don't do that, right? This is how you build it from source. And yeah, if you don't have a GitHub account, the easiest way is to use HTTPS instead of the SSH git clone. And then it works, yes. Okay, anybody else?
Question. So the commented command is if you don't have a GPU?
Correct.
The last one.
So the difference between the second last and the last line is just that one has _ CUDA 80 and the other one doesn't. And if you don't have a GPU on your laptop, and I guess you would know it, and that applies to most people, use that last line, right? Okay, so now we should be good. So SSH, and then whatever key that you need to use, possibly, and then this is essentially the magic sequence. This sets up port forwarding. So -n -f -l, localhost, port number, remote host, port number, as in. So basically localhost colon 8889, localhost 8889. That's what you need. Yes, let me try that. That sort of kind of works, but then it rolls over on the sides, right? If you don't know how to do it, a quick Google search for Jupyter Notebook port forwarding will actually get you to the page that has the instructions in detail. So just if you need to log into some remote machine.
So you don't have to do this if you are using your own Mac?
Pardon?
You only have to do this if you're remoting onto a machine?
Yes. So I'm doing this right now because I want to be able to show off some GPU features on the notebooks. And since I don't have a double GPU on this machine here, because it would eat way too much power, I'm basically SSHing into an AWS instance that has this. So in this case, I'm actually picking a G3 8X large. That's probably overkill, but I wanted to have something with 2 GPUs that's reasonably swift for the demo.
Can you show what AMI you use?
I built this from scratch with the NVIDIA drivers yesterday. We have an AMI that has some of this, but it's not on the latest NVIDIA drivers. That is about to come very shortly. This is why this may not work right now, so I apologize. But what you could do is, actually, let me quickly get to that. Okay. So if you go to bit.ly deep Ubuntu and just grab any CPU instance, that will get you most of the setup running right away, but GPUs will be iffy. Right? That's the only thing. That's because of exactly that driver issue. So just pick like a C4 2x large, and then just MXNet install -- pre. So pip install MXNet -- pre will get you there. Okay. Good. So I'll probably move on. In the meantime, Zach is actually there, and just wave at him, and he'll help you get things set up. But I don't want to bore everybody else with installation details for the next half an hour. So one thing that I learned is there are some groups where a lot of people use Windows. So at ICML, we basically had nobody asking for a Windows support, which is why we failed so miserably at that today, so I apologize. Okay, now, this is the other part that you should clone. So take a picture of this. So this is this poor imitation of a camera. So git clone, and then Zach chase MXNet the straight dope. Or if you go to gluon.mxnet.io, you will actually find a pointer to that link anyway. So because that has all the notebooks. There's way more notebooks, around 40 of them. This is growing at probably 1 or 2 notebooks a day of essentially teachable material to learn deep learning from scratch. And we'll be using some of this for the tutorial today. Yeah. This is the Amazon Linux version of the deep learning AMI, and that's the Ubuntu version. That one's a little bit more wieldy. Okay, good. So then let's get started with the actual stuff. Good. So yeah, I mean, you can basically SSH into the deep learning AMI, and it has a lot of other things installed as well. So it does have, the CUDA compiled versions of MXNet, but it's a slightly older release because we basically, use point releases of most of the toolkits. So if you want to have Keras or TensorFlow, whatever. So within 1 month, we basically compile, build, and link against it, so that should work. And yes, so you can also do TensorFlow. So if you're going to the TensorFlow tutorial, you know how to start that, right? And yeah. Okay, I guess that's for Zach. Okay. So let's start with Deep Learning 101, and this is really simple stuff, right? So first thing is supervised learning. I guess we all know what that is. So we have, some images and video and audio or text, and this goes through some function, and then something comes out of it, right? Or you have some action or whatever. And so, well, now if you think about how do you program, how do you write code? Well, you hire a programmer, and they have a beard, and they take data, and they write a function, and then something comes out of this function, right? And so the question is, why would you do that, right? Because, there are some limits to what you can do with a conventional program, and that's usually, when we don't know the exact rule of how to go from input to output. And while your 2 or 3-year-old child can usually tell a meow meow away from a wow wow, writing that in a piece of JavaScript is not fun. As in, I would dare you that you can't do it. So, programming with data, well, again, we have all the core components are input data, targets, and model, and loss function, and so on. And then, by having all those pieces, well, you basically run your favorite machine learning algorithm that picks among, the parameters of your model the right thing to do. Okay. So why am I belaboring all of this? There's this wonderful job interview that Joel Grus had with Google. Actually not so wonderful for him because he actually didn't get the job, but you should absolutely read his blog post. So there's this children's game called FizzBuzz. And this game called FizzBuzz is basically something to teach kids how to divide by 3 and 5. You basically count up, and you count up 1, 2, fizz, 4, buzz, fizz, and so on, right? And the interview question was, please code up FizzBuzz, right? And, FizzBuzz coded up is fairly straightforward. It's, 5 lines of JavaScript, right? So he probably didn't feel like the interviewer was taking him very seriously. So he thought, okay, let me actually show off how to do that in machine learning. The interviewer didn't think it was quite so funny, but he's written this up brilliantly. I mean, it's a joy to read. In any case, so he went on to generate some training data like 9 fizz, 10 buzz, 2 output 2, 10 output fizz buzz. And then he designed a feature extractor, and of course he cheated in designing the feature extractor because he basically extracted as the features whether it's mod 3, mod 5, and mod 15, right? Duh. Okay, and then, he armed with training data and, the features, he trained a classifier and mapped the input to output using this training data. Turns out he got like 95% accuracy, so maybe that was the reason. But, I mean, joking aside, why would you do this? Well, and the reason is really, if you don't have this proper dependence, then, if we program with data, we're really taking data, images, text, sound, video. The goal is to learn this mapping. Mind you, there are things like a loss function, which sometimes people ignore. So, for instance, if you want to classify truffles and death caps, I mean, not that they look terribly similar, but they are the mushrooms that look very much like death caps, then just classifying things correctly or with high accuracy doesn't necessarily cut it in terms of what you're going to do. Because even if there's a 1% chance it's a death cap, you will probably not eat that mushroom unless you're crazy, right? Because the loss function is highly asymmetric. It's called death cap for a reason. It will kill you if you eat it. Whereas if you don't eat it, well, okay, what's one mushroom dish less that you've eaten in your life, right? So loss functions are quite an integral part to this, right? So now, with that background, okay, why do we actually call it neural networks or deep learning? And by the way, this is not where it started from. This is the Phrenological Society journal from 1948. This is where it started from. So this is more like the 60s or before that. So this is a neuron, right? And so just in case you ever wondered why is it called neural networks really, well, there's actually a very close match to where the perceptron and everything started from. So you have this cell body, and what it does is called soma, not south of market, but it combines all the signals. Then you have dendrites, that's like the input bus, which grabs signals from other places. Synapses, which are the interfaces, which basically adjust whether things are up-weighted or down-weighted. And then there's an axon, which is essentially a ginormously long cable that goes from that cell body to somewhere else where that signal needs to go. How do we know that those cables are really long? Well, I can wave my leg, and what happens is a signal goes from my brain down there, and it basically goes through one neuron, right? So this is maybe 2, but basically these are long signals. Okay, fine. So here's a mathematical model of a neuron. We basically have inputs, x1 through xn. And then you have those synaptic weights, which basically weigh how much that input should be adjusted. And then you sum this all up, and you get some function, which I'm now using linear algebra notation to write it, namely w.x. Okay, fine. Now, of course, that's not the full story, because if we want to turn this into a classifier of cats and dogs, well, that real number needs to be mapped into something between 0 and 1, namely the cat probability or the dog probability, depending on whether you're a cat or a dog person, right? And so we have basically that other sigmoid nonlinearity that's followed by it. Now, training your neural network, in this case it's a single neuron, is basically you learn the weights and the bias. Now, you might think, well, this is utterly boring. Well, actually, this is sort of the basis of a lot of kernel methods that were quite popular in the 90s and early 2000s. What basically they did is they made this one single neuron super fancy. What neural networks do is they keep the neurons dumb but take plenty of them. And there are computational reasons why one or the other is better at different times. Okay, so back to our perceptron, and now let's actually have a look at some code, right? So this is the perceptron to classify cats and dogs. And if you think about it, if you first extracted some ImageNet features, then actually a linear classifier will do quite nicely for it. So let's actually look at what our perceptron looks like in a notebook. There we go. And oh my God, the network is slow here. I apologize. In case I can run it locally. Okay, so we are going to get to a lot of the details, and there's text to it, and you can read that text later. So this is, by the way, this entire thing is meant as not just a notebook, but also effectively an interactive textbook that we are currently writing, so you can use it for teaching purposes in your class. And obviously, git, clone, modify, contribute back, whatever. So it's a bit of an open source experiment in book writing. But okay, we'll get to the details in a moment, but this is essentially the standard import ritual of what you would do to start up MXNet. And since I don't like typing long terms, I'm going to just use import MXNet as MX and ND array and autograd, right? So the next thing I need to do is I need to actually generate a classification problem, and there's a couple of useful helper routines. They are mostly just Numpy and whatever. So I'm not going to bore you with this, but basically what it does is it generates some fake data, and if you look at it, you see some red dots and some blue dots, and they're separated in some way. And this function getFake will do that for me. So if I were to run it with 100, right, then we'd get 100 points. And of course, we want 2 dimensions because otherwise it doesn't look nicely. If I were to run it again, it would generate some other random set of 100 points. And this term here is basically how large the separation between them is. So if I change that to 0.01, then I'll get something that's much harder to separate, right? There it would be really hard to draw a line of separation between the sets. And so you might think, well, that actually makes the problem harder, and indeed, there's some math that, as we'll see afterwards, shows that this will actually make the problem harder to learn. Okay, let's draw one more. Okay, so here's the data. Now let's define a very, very simple algorithm, and I'll walk you through the slides in a moment. But this is the simplest machine learning algorithm that you can think of. And don't worry about the nd.dot notation. That's just the dot product, and I'll explain shortly what it means in detail. But here's what the algorithm does. So nd.dot of w and x plus b is really inner product between weights and inputs plus bias. And I'm checking whether this is greater than 0 for y equals 1 or less than 0 for minus 1. And the easiest way to check it is to just look at the product of these two terms, right? Y times nd.dot plus b, and check whether this is less equal than 0. If this is less equal than 0, it means I'm making a mistake. And if that's the case, here's the world's dumbest update rule. Well, second dumbest because you could do it without the bias, but basically all I do is I just say weight equals weight plus y times x. So just add the erroneous example to my weight vector, add the erroneous label to my bias. So you can clearly see what that does to the bias. It just shifts everything in the direction of the bias. It shifts the weight vector in the direction of what I got wrong. Okay? And just for convenience, such that I know whether I made a mistake or not, I'm just here returning a 1 if I made a mistake, and a 0 if not. And that's just for plotting purposes, because I want to see whether it works. And this is really just, basically matplotlib plotting and telling people whether it works or not. Okay, so let's actually see whether this algorithm works at all. And the full training loop is now nothing else than, go through the data, the x and y pairs, and I'm doing that in Pythonic notation by just zipping the x and the y vectors together and iterating over them jointly. And I just update, I run the perceptron on the parameters. Okay, so let's see what happens. And okay, so let's actually see what's going on here. Well, what may be hard to squint is that there's this point here which you got wrong. And you see the contour plots, but you would see that nicely on your own laptop. And every time it makes a mistake, it shifts and updates terms, right? And after a while, okay, some more updates. It actually gets it to a position where it separates all the data accurately, which is here. Okay, so if we look at that closely, we see this, thin cyan line, and it says actually 0, because that's exactly what this function is, 0. And you see that all the red dots are just to the left, and all the blue dots are just to the right. It's not necessarily the most beautiful one, so any of us would have probably drawn something a little bit more centered, and that would have been close to the large margin separator, and that would give you a support vector machine solution. But since we just care about actually separating the data, even if just barely, that's all we want. Now, why does it matter? Well, there's actually a nice theorem, and I'm not going to prove that to you, but I'll show you afterwards on some slides in a bit more detail, which basically says that it takes at most as many updates as it's basically the square of the radius that encloses all the data divided by the square of the margin of separation between the data. So in other words, if the data is very well separable, it doesn't take a long time. If the data is really spread out, it takes a long time, and you can easily see why that ratio matters, because I can always squish everything together to a unit ball of radius 1, in which case it's just 1 over the margin squared. But rather than showing you the theorem proof, and there's actually the proof on the notebook, and I'm not going to inflict that upon you, is I'm actually going to briefly run this, basically 10 runs of a perceptron for a large number of ranges, and what we should see is basically the number of updates it takes. And yeah, not quite sure why it's not showing yet. Okay, it's taking a bit longer. Maybe I didn't code it up very efficiently. Let's actually look at the slides in the meantime, and we come back to this in a moment. But what I just walked you through to some, okay, well, let's go to this first. So here's the Perceptron algorithm again in its full glory, right? By the way, there are plenty of seats in the front if you want to move in. And yeah, we'll get to more technical parts, don't worry. Basically, this is just the Perceptron algorithm written out, now a little bit more easy to read. The convergence theorem, which is basically radius of a margin squared, and the important thing is it's dimensionality independent. It's order independent as well. It's just, it counts the number of updates, not the amount of data that you see, because every time you are confirmed in what you're doing is right, you don't change anything. And now, here's an important detail, and you may have wondered, why did you see this weird, white wolf avatar on that slide, right? So this is actually a game called Black and White that Peter Molyneux did about, I think, 20 years ago, maybe longer ago. Probably very few in this room will remember that game for two reasons. First of all, it's a long time ago. Secondly, it wasn't such a great commercial success. And so what happened? Why am I bringing this up? So basically, in this game, this is the first occurrence that I know of where somebody tried to use machine learning in a computer game in a non-trivial manner. And so to understand a little bit what happened there is, basically in this game Black and White, you played God, and you had an avatar, in this case a wolf, who would try to mimic your behaviors. If you were a good god, the wolf would also be good, but if you were evil, then the wolf would also be evil to all the villagers. Now, how would the wolf or a monkey or any other avatar creature learn whether you're good or evil? Well, it would basically look at a classification problem where various context variables, given those, it would try to do the same thing as what you did. And the way this was trained was using a perceptron. And so you might already wonder, whether that's really a good idea. And the reason why this may not be a good idea is because people are rarely quite as clear-cut, where it's completely clear whether you, in this context, play good or evil, right? And the perceptron convergence crucially relied on things being nicely separable. So what happened is this poor perceptron tried to separate something that cannot be separated because people aren't quite that clear-cut. There's some idiosyncrasy in their actions. And so the entire weight vector started diverging, and the avatars became increasingly difficult to handle and to control. And that was one of the reasons why the game actually didn't happen to be quite such a commercial success, because the avatar was insanely hard to handle. I probably spent too much time on that game. And now we should actually be ready to look back at the notebook. And it should be nicely converged. Yep, there we go. So what you see here is a curve. And now I should probably tell you what's on that curve is this is the number of updates. And this is the width of the margin. And this is averaged for every 0.5, 0.025 changes in the margin. So basically the difficulty over 10 runs. That's why it took a while, because this was hideously inefficiently coded up and also doing a lot of tests, right? And so what you can see is, obviously, the wider the margin, right, the fewer updates you need. So the quicker the algorithm actually learns. And the theoretical bound is somewhere above there, obviously, because you will never have more updates than what the theory tells you. But in practice, life's actually a little bit nicer to you because your data is a little bit nicer, right? This is another reason why you should never use theorems to actually guide your algorithms in detail for any practical parameter tunings. Theorems are like seatbelts. You need them, but you don't want to use them for driving, right? I know some people here in the room will disagree, but I have tried very hard and usually fail to design theorems that are perfectly tight for all practical cases. Anyway, so this was the perceptron. Now let's take another baby step towards maybe the 60s, early 70s, namely the multilayer perceptron and backprop. Right. So here's a perceptron. And we've seen this before, the output should be on top, of course, and we decided to flip inputs and outputs yesterday, and I guess not everything got flipped in time. But anyway, so you have the output y of x equals sigma of w dot x. Right. Now, a multi-layer perceptron is just that, right? You basically take the input, you process it, you get some output. You use that output as the input for the next layer, right? And then, of course, 2 layers are better than 1, and guess what? 3 layers are better than 2 layers, right? And so you basically stack things up on top of each other. Now, there's this thing called sigma here, which sits in between all of those, and this is some nonlinearity. And so the first question, of course, I have to ask everybody is, so why on earth do we actually need this sigma thing, right? Why can't we just happily live with one linear function after the other? What would go horribly wrong if we didn't have sigma? Any suggestions? Yes? Exactly. So if I have a linear function of a linear function of a linear function, then that's still a linear function. Now, to my embarrassment, like 2 weeks ago, I was in a terrible hurry, and I actually forgot some nonlinearity somewhere and just quickly wanted to code something up and then ran it and then realized, well, it wasn't working. And then only afterwards I looked at it and realized, oh, I had forgotten the nonlinearity, right? So you find out the hard way this way. So this is, make sure when you build your deep network, you remember that, because otherwise things become embarrassing, as I found out myself. So let me just rewrite this, and because it's kind of painful to draw individual neurons, and that gets really painful with very big networks. So let's draw it a little bit more simply. So we basically have, some input x1, and then some weights, and then, which becomes an output, and then input to the next layer, x2, x3, x4, and then y. And what I'm going to do is I'm basically going to treat each such transformation as a separate layer. Your learning framework of choice may not implement it this way. It may actually combine several of those pieces into one for computational efficiency, but it does that automatically. You don't have to worry. So no matter how you specify it, it'll fuse the operators quite nicely together. So this is actually done for efficiency, but basically you have some function, right, that takes an input x and produces an output, which is then the input for the next layer. In that sense, the loss function, which takes the labels and the output of the ith layer, is just another layer. And so now the obvious question is, how do we tweak our parameters? And one very easy way to tweak it is by just doing gradient descent. So in other words, take the parameter, update it in the negative gradient direction. Okay? So this is, chain rule. And after the backprop, I think we all deserve coffee because it's 9:30 now. It's basically what you do is you just write out, so I'm just writing out formally, xi plus 1 is fi of xi and wi. And then you go and write out some gradient, and of course you use the chain rule where basically f of g of x is f prime of g of x times g prime of x. So now let's write this out in detail. So because we have now weights for potentially every single layer, if I just have a nonlinearity, I don't have a weight there, then of course those terms go away. But so if I want to compute dw1 of x2 of x, well, that's of course dw1 of f1 of f of x1 and w1, right? And I'm done. This gives me the gradient with respect to the first set of weights. Now, if I want to compute the gradient of a two-layer network, so I have x3 of x, so dw1 is basically now applying the chain rule, dx2 of f2 of x2 and w2 times now dw1 of x2 of the x. That latter part I already got, right? And obviously, taking any derivatives with regard to W2 doesn't really matter if I'm only after the gradient with regard to W1, because W2 doesn't really depend on W1, right? It's only in the x's where all the dependencies on the w's happen, and the w's are just the parameters at that appropriate level. Okay. So more generally, what I get is that dwi of xi plus 1 of x, well, that's just this term here worked out. And if I do that for any xj with an index larger than I, then I just need to work my way through the chain rule, right? This is, nothing terribly fancy, but what really happens is I have activations going one way and the gradients going back the other way around. Now, why am I belaboring this? Because, hey, look, every high schooler knows the chain rule, because it actually has some very nice implications in terms of how you optimize, right? So the first reason why this influences how you optimize is because there's actually quite a difference when you run a deep learning code between training and inference. Because during inference, and inference is really a misnomer, it shouldn't be called inference, but somehow everybody in deep learning has picked that name for deploying it and running it at test time, is you only really need the forward pass, right? And you can just compute one of the values after the other and throw everything else away. This is like running your computer program in the way it was intended to run, right? Now, we all know if we run a computer program with a debugger and a stack trace and everything in there, it requires a lot more memory. And this is exactly what happens during backprop if you think about it. You basically look through the entire trace of the program and you work your way and perform a dependency analysis through it. As a matter of fact, this is exactly what AutoGrad does, and I'll show you that in a moment. Because you can actually perform gradients, compute gradients through pieces of code. So as in Zach will show you that after the break. So basically, this is backprop, just fairly straightforward, and you just run this through. The good news is you actually don't need to know this if you're using something like MXNet or any other deep learning framework. They will do that for you. Some of them will make it opaque to access it. Some of them will make it easy. MXNet falls into the latter category. Now, let's just do this by hand once, right? So if I have a sigmoid, this doesn't have any weights, and I just apply the gradient to each of the coefficients explicitly. Well, that's straightforward. For a fully connected layer, well, I have weight matrix times vector, and you get the corresponding gradients, and that's also straightforward. And just to belabor that point, MXNet will happily take care of all of that for you, and after the coffee break, we'll see how this is done. So just to give you a little bit of a taste of what is to come, so you basically can define a network, for instance, by just adding the layers on. You could also write some piece of code here that does interesting things, and we'll show you both ways. But you basically add a layer, like a dense layer. And here I already specified a nonlinearity. Here it's called a ReLU, rectified linear unit, which is nothing else, the max of 0 and the function value. But if you call it ReLU, you can write the paper. Then you, perform this thing called dropout, which is basically nothing else than randomizing the input to the next layer. And dropout sounds so much cooler again. You have another nonlinearity, you have another dropout part, and then you output things. One fairly interesting thing, and then in the end I have some loss, and okay, maybe we should have picked a shorter name than softmax cross entropy loss, but whatever. Here's really what's going on, right? So this network, when it's instantiated, doesn't actually know about the input dimensionality of any of this yet. It will do that the first time data hits that network. That's when actually all those things become instantiated, all the variables become populated. We do that automatically for you.
So Alex will be running around. How many people here are just getting here? All right, so Alex is running around. So if you're having any trouble getting started, you might want to flag him down. Basically, you can, if you have especially a Mac or a Linux device, things shouldn't be too hard. You can pip install MXNet to follow along. You want to use the -- pre flag when you install, because we're teaching some features that are not yet in the latest stable release of MXNet, but will be forthcoming. If you're just getting here, I'll just kind of walk through kind of very high level crash course on how deep learning works and how backpropagation works, and kind of got people up and running, installing. And now we're going to take maybe a more implementation-oriented and practical dive into MXNet. We're going to start by going towards the kinds of data structures that we're going to need to work with. It helps maybe to just provide some context again about what these data structures are going to represent. So basically, we need linear algebra. We need to be able to do it fast to deal with deep learning, and because this is more or less the kind of structure of a neural network, is that we're going to have some kind of function which is going to take some input. So we need a data structure to represent our input, and some parameters W, which are often matrices or vectors, or even like higher order tensors in the case of convolutional neural networks. We're going to compose them together in some way. So that's going to involve a lot of multiplications, which is going to require us to have high performance linear algebra library. And then ultimately, we're going to compute some loss, which is going to involve yet more, usually element-wise operations on the results. We're going to need to take derivatives, which is going to involve yet more multiplications. And then finally, we're going to perform a gradient update. So we need sort of an appropriately fast library to accomplish these things. So MXNet deals with this through what's called ND-array. You might recognize the name ND-array from working with being the same name for the primary data structure for working with Numpy. This is not a coincidence. So basically, we want to provide a lot of the functionality of Numpy. Numpy, if you're familiar with it, is a kind of amazing tool that I think has been sort of revolutionary in open source scientific computing. So it gives you a lot of great tools for manipulating vectors and matrices and scalars and performing kind of arbitrary linear algebra operations. And it does a great job as long as you're sort of running on your PC or on CPU on a single workstation. So there's a few, you might say, like, why don't we just work with NumPy? For example, in a lot of declarative languages, you might use NumPy as your primary workhorse for doing imperative programming, and then you just feed things in and out. So there's a couple of reasons why. One of them is that when you kind of have to convert back and forth between one library for holding your data and then another one that you do the processing on, these conversions are actually quite time consuming. So it prevents you from doing kind of a lot of smart things with scheduling your operations. Another reason why is that you want to run on really fast hardware. So I don't know if anyone has tried running even an MXNet on a laptop, but it's not fun, and it might take you about a year to get a result, and by that time you will have quit machine learning and moved on and found something less tiring to do with your life. Another thing is that NumPy doesn't provide source support for automatic differentiation. So remember, the important step for the actual learning part of machine learning is performing these gradient updates. So we need to be able to actually take gradients in order to perform a gradient update. If you want to do this in NumPy, you might have to actually work out all the derivatives by hand. And that's quite possible, and that's what people did for many years. But a relatively small change in your model could actually make quite a big difference in the gradient calculation. And so basically, you could spend an enormous amount of your time just doing arithmetic, and that's not really the exciting part of modeling. So having automatic differentiation allows you to basically, you write the model, how is your output generated from your input, and the library does the rest of the work for you. So MXNet's ND-array, so this is in just, if you go from MXNet import ND, provides support for sort of arbitrary devices. So it's optimized to run on CPUs. You could run on GPUs. You can have parameters that are spread across multiple GPUs or multiple machines. So it's easy to work with distributed systems. It's also, and we don't talk about here, but it's also set up to compile well for working with like Internet of Things type things. So like one of our a colleague of mine, Aran Khanna, works a lot on edge devices. And another really exciting thing about MXNet is that it's non-blocking and does lazy evaluation. So what's cool about this is since you're working, if you're working in an environment where you only have one processor, it's maybe not so important to be lazily evaluated or non-blocking. But if you're working in a system where you have, let's say, multiple GPU cores or multiple GPUs or multiple machines, each of which have multiple GPUs, then it's really great to have lazily evaluated code. So basically, if you have imagine you have two giant matrices, A and B, and you want to multiply them. And then you have C and D, and you also want to multiply them. And at some point, you want to combine the results. So we'll call those E and F. So you could say E equals A times B. And no matter how big these matrices are, MXNet is going to say, OK, what's next? So from a Python perspective, you execute this command, E equals A times B, or dot B. And immediately, control is going to return to the Python execution environment. So deep under the hood, which is not really the purpose of today's talk, but there's some cool articles written by our primary architect on this, Mu Lee, MXNet actually has a really sophisticated scheduler that is doing these smart decisions about, here's a calculation that the user wants to run. Do I have available machines where I could run it? And does it depend on any results that have not been calculated yet? And if it's possible to run this, then it's just going to send it off. So you can run A times B and C times D simultaneously, and then combine the results. Yeah, so the way we work with device context in MXNet is we can set it explicitly using basically, like we can access the context just through the global namespace. Say MX, if you port MXNet as MX, then just MX not CPU is going to be the sort of Python object corresponding to the CPU. You can get, if you're on a machine with multiple GPUs, you can have GPU 0, GPU 1. You can have a list with all the GPU context. And given an ND array, you can very easily copy it to another context. So basically, you want your data to live on the device where computation is going to be done. So in the case of a neural network, a common setup is that you might have too much data to keep in main memory on the GPU itself. On the other hand, you have enough memory to store usually the parameters of your model. So a common setup is you'll have your parameters live on the GPU, and then when you pass in new data, you can send it to the GPU by basically copying it to that context. One issue with copy to is that you make a copy. And making a copy is not a particularly smart thing to do if it so happens that your data already lives on that context. So MXNet also provides the as-in context function. And this is sort of does something smart, which basically says, imagine that you're writing your software and you abstract away that I'm going to have a variable that stores the location for the data and the location for the parameters. And when I work with a small data set, maybe I'll set them both to be the GPU. When I work with a gigantic data set, but a reasonably sized model, maybe I'll say the parameters live on the GPU and the data lives on the CPU. In that case, you don't want to copy from the GPU to the GPU. So as in context, we'll sort of make a copy only if necessary, if you're not already on that context. So I don't know if you remember the sort of high-level picture of how declarative programs work and how imperative programs work. So remember, declarative programs are what you're familiar with if you did. Like I grew up, the first library I encountered was Theano when things started going crazy in 2013. And declarative, right, is it's sort of obvious how you do gradients because you basically say, here's my entire plan. I'm going to feed in these inputs. You're going to go all the way to the output of the function. And you're going to say, and I'm going to want the gradient of the output with respect to the input. So it knows from the very outset how does the output relate to the input because it's built this graph. So the question is, how do we build a graph without building a graph? So autograd, right? So if you look at like this, when we say y equals x times 2, we're actually multiplying x times 2 and assigning that value to y. If this were NumPy, then NumPy wouldn't know at that point. It would know the value of y, but not where it came from. And so if you then want to take the derivative of y with respect to x, it would say, well, sorry, you're out of luck. I don't, for all I know, this value came from God and not from X. And you'd be hard-pressed to produce evidence to the contrary. So what we do basically is you could think of it as we have a tape recorder. So we don't always want to remember all the information about what has happened, sort of the history of where everything came from. But sometimes it's really important. And specifically, it's really important if we're going to want to take gradients later. We need to know what is a function of what. So what we do is imperative programming is basically, so say we have this array x, which has some value assigned to it. We're going to want to take a gradient with respect to x, but not necessarily every intermediate value, right? So in this case, maybe not with respect to y. So z is, say, the ultimate quantity that we want to optimize, and x is our parameter. Then we don't necessarily want to take a gradient with respect to y, but we do want to take a gradient with respect to x. So what we can basically do is we call attach grad. So attach grad does two things. One is it allocates memory for a gradient with respect to x. Because x has 4 components, the corresponding gradient also has 4 components. So you'll see this again, and I'll hammer it home when we actually look in a proper notebook. But it's good to sort of internalize these things. So basically, initially that's going to be all zeros because there is no gradient of what. If you called an optimizer on it, you wouldn't want it to actually update the value of x. We haven't specified any kind of objective. The other thing that attach grad does is it lets MXNet know that we're going to want to take a gradient with respect to this. So then when we calculate some new value, that's say our objective, we place it inside an autograd.record block. So in this case, we've imported autograd as AG. So basically, we just start a with AG.record block. And this block just says, hey, I'm going to want to take gradients based on what happens inside this block. So typically, that computation is just going to be like feed the data through the model to generate output, feed the output in the label into the loss function to generate a loss or something. If that's new to you, don't worry, we'll go through it in the machine learning context. But in its generic context, this is what happens. And so you might say, well, why is this any cooler in the imperative context than in the symbolic context? And the main reason, what's really cool about autograd in imperative is that you can calculate your output using sort of arbitrary native language control flow. So for example, here we just write a Python while loop. And that while loop can even depend upon things that change dynamically in Python on every single forward pass through the neural network. So declarative, remember, you get some optimization advantages, but you have a huge cost in terms of flexibility. But in the imperative setup, you could do really arbitrary things. Instead of saying while nd.norm, you could say if it's if it's 3 o'clock, if it's between 3 and 3:30, then make this calculation. Otherwise, don't. Or you could have a web application where, depending upon the state of the user, you want to use a different parameter or something, and you could check these things dynamically. Anything you could do in Python, you could do in building your network. All that matters is that ultimately you produce some value, which is whatever happened in the middle arose through a bunch of ND array functions. So I think, whoa. Is Alex here? Is there a reason why this isn't clicking? Hmm. All right, there we go. What? That's weird. I might have messed up that link. Yeah, OK, so just to, if you're really familiar with Numpy, this might seem a bit repetitive, but we'll get through it quickly. So right, what's going on here is these are all the import statements we need to just start messing around with ND array. typically we'll import MXNet as MX just because it's kind of convenient, and a lot of things do live in the global namespace. And we'll import ND array. So if you want to say just allocate some memory and you don't want to even incur the overhead of any kind of initialization, even zeroing things out or setting them to 1 or whatever, you could just call empty and specify a shape. ND array supports the common zeros and ones functions for initializing a new matrix. We have probably at some point there will be a reorganization of the namespace so you don't have these underscores, but to instantiate a matrix that has sort of from kind of like independent Gaussians is also quite easy. So it's quite convenient that it supports the Numpy API. So anything that you could do, not anything, but generally if you don't know how to do something, you could in your head just say substitute Numpy for ND array, and it'll work. So things like grabbing the shape of a tensor also works in a familiar way, and also getting its size. It also has the same sort of element-wise operations defined that you're used to, like addition and multiplication, exponentiation. And we can calculate dot products quite easily. Maybe it's... You also find that, here, where are we? Yeah, so again, sort of everything kind of works the way you expect it to. You also have a lot of the data generating functions like arange that you might depend upon. The good thing is you basically don't want to have to convert between NumPy and ND array for 2 reasons, and that's why we try to support as much of the NumPy API as possible. One reason is because it's slow. It's slow just in and of itself to do the conversion. The second reason why you don't want to convert to NumPy all the time is because ND array, remember, is really smart. It does this lazy evaluation. NumPy is not smart in that particular way. And so basically, if you say, I want to take a value and convert it to NumPy, at that moment, that's a blocking operation. Like, you can't keep going in your code executing all kinds of other things that come after that until something's been converted to NumPy. So we want to make sure that, say, when you write your evaluation loop, you don't have to check the metric in NumPy. Because basically, you could be having, say, okay, you want to say you're doing an evaluation loop. So you want to calculate the score on one example, and then immediately afterwards, Python can try to calculate the score on the next example. And remember, the scores on the various examples do not depend upon each other. So it could just start throwing these things at GPUs like crazy. But if it calculates the score on the first example and then has to convert to NumPy in order to, has to, do ND array to make the calculation and then convert to NumPy to get the score, that's kind of crappy because then you're sort of stuck waiting for NumPy to finish before you can move to the next operation. So yeah, again, right, getting, you can call length, you can call shape, multiply matrices together, transpose is defined in the familiar way. Same for sort of like high-level tensors. Norms are also defined as you might expect them to be. Yeah, so probably, I guess, won't get too deep into, I don't know, how many people here don't know what a dot product is? So, okay, although that's kind of an unfair question because, I don't know, you raise your hand. But, so, yeah, matrix-matrix multiplications, you can just call a dot operation as well. Calculating norms is something that's obviously quite important if you're going to be defining neural networks, because often our objectives are sort of defined in terms of norms. Like we want to minimize the distance between certain vectors, whether it's a regression target or like trying to push certain embeddings together. And for the default L2 norm, you can just call nd.norm. Yeah, so I think let's move on to autograd, which is perhaps. And how many people have programmed with, have not programmed with an imperative deep learning framework? So like maybe you've used Theano or TensorFlow, but have not used a either the bleeding edge MXNet or PyTorch or Chainer. Yeah, OK. So this actually might be a little bit new to some of you. So let's go through it. So basically, we're just going to add one package that we import in Autograd. So when you do Autograd, we're just going to import the Autograd package. And remember, say we want to take a derivative at some point with respect to x. So we're going to instantiate x. This could be a parameter in a model, but it could be basically anything with which you want to take a derivative. The next step is you want to call x.attachGrad. Yeah? Oh, increase the font. That's a good call. Is that a little better? I wish there was a way to like move the menu to be less wide. But great. So if you guys are running it in the IPython notebook now, you could just call like x.grad. And you'll probably see after calling attachGrad that you'll get all zeros. Which is sort of what you want, right? If you were to try to do something like perform a gradient step on x without actually having calculated a gradient, you'd want to have that be a no-op. So now, if we want to take a gradient with respect to x, right, we can just call autograd.record. And this basically says, hey, from this point on, this is where the relationships that define the compute graph are going to be defined. So don't forget what's happening here. So we calculate y from x, and we calculate z from y. And then basically, now the compute graph exists. At this point, we can already exit the record block. So we don't need to be inside the record block to actually calculate the gradient. We just need to be inside the record block to build a compute graph. Once you have a compute graph, then you can take a gradient. So we can then sort of go out of scope and call z.backward. So this is sort of the standard flow that, working in any kind of imperative interface is basically you're going to have some parameters that you're going to want to model, that you're going to want to learn. You're going to have some kind of objective function that you're going to calculate using those parameters and probably some data that comes from outside. In this case, we don't actually have data from outside. And then once you calculate that objective, then you're going to want to call backward. Backward basically is going to populate the grad field. So if you call grad again, whereas before you had zeros, what you're going to have instead are the actual values of the gradient with respect to each component of x. So I imagine that's what you have if you're running in Jupyter. And there's also something called the head gradient, which basically is, it's a little tricky, but basically the idea is that when you're doing backpropagation, right, say you have some intermediate layer, you're going to take the gradient of the loss with respect to the activations of that layer, and then to take gradients below, right, you take, right, like dz dx is dz dy times dy dx. So you're basically calculating the dz dy part, right? The sort of all of the backwards propagation that has gone up into that point, and passing it into sort of the function below it. So if ultimately what you care about is dy dx, then sort of like y dot backwards is going to receive as input the head gradient. Most of this is happening under the hood. So you don't actually have to think about the chain rule, and you don't actually have to think about head gradients. But essentially, like the machinery is powerful enough that you're sort of seeing more or less the same machinery here that is actually taking place under the hood. So if you wanted to like do something explicitly to mess with how the chain rule is performed, you could go in and start janking around with the head gradient, but it's really not necessary in order to follow any of this material. And just again, right, this is the example from before that you could even, if you're in the Jupyter notebook, kind of mess around and write your own arbitrary Pythonic statements and just confirm for yourself that you can really do anything inside this calculation and that affects the model or that doesn't, and still take a gradient at the end of the day. OK. All right, so we have a data structure that we can use to represent our model parameters in our data. We know how to do kind of basic operations like sort of common linear algebra functions. And we know how to take gradients. And these are really, I think it's kind of sort of the, not to use the word miracle, but I guess it's sort of the kind of miraculous thing about deep learning, I think, is actually that not really how powerful it is, but how simple it is. That this really is all of the sort of core primitives that you need in order to go build your own, even something seemingly quite complicated or fancy like LSTM, recurrent neural network. This is really all you require. So let's take a look maybe now at some actual models. So we've spent some time kind of getting familiar with the machinery. So let's work our way through linear models and multilayer perceptrons. So linear regression, sort of a classical statistical model. I think it might even sound weird to some people that we describe it as machine learning, since it probably predates the term machine learning by quite some time. And basically, the idea of the model is we want to predict y from x. So y is going to be some real valued target, something like predict the home price or something, where it could take sort of, well, in that case, probably a positive real value, hopefully. And the loss function sort of makes it linear regression is that we're going to use a squared loss. So basically, for every model, we have a loss function. This is basically how bad is our model with respect to the target. And sort of the linear for linear regression, the squared difference is the optimization target. And the optimization algorithm, again, remember that we're going to use in order to update it is stochastic gradient descent. So stochastic gradient descent is this really powerful tool that basically says we're going to feed through our data. So maybe we should zoom out. So what makes it, if SGG is new to you, so the more naive thing to do is just gradient descent. So gradient descent without the stochastic part would say we'll take our entire data set and we'll calculate our fitness function, our loss function, based on how close all of our predictions are to all of our targets. And then we're going to update the parameter so that we reduce the loss sort of on average across the entire data set. So the reasons why gradient descent is not so great is that if you have a gigantic data set, then you might be in a situation where passing through the entire data set once is going to kill your day. And in that case, if you have a model where that first direction of the gradient doesn't tell you all that you need to get all the way to your value that minimizes it, then basically you get to take one step and then you're done, right? And actually, to perform gradient descent usually takes quite a bit more than one step. So it turns out that what you can do is you can basically say, I'm going to just get an unbiased estimate of the gradient. So it makes it stochastic because you say, I'm going to grab some data point at random. So I have a data set that has a trillion data points because, I don't know, because I work at a big company. I'm just going to select one of those points at random. That's the stochastic part. And because the loss function that we're worried about happens to be an average over the data set, then the loss on any one example selected at random is an unbiased guess of what that is. What we actually do in practice is what's called mini-batch stochastic gradient descent. So batch being I'm going to run through my entire data set, and sort of pure stochastic gradient descent being I'm going to select a single example. What we're going to do is we're going to select, basically what is enough examples that we get to take advantage of the parallelism that we have because we're working on a GPU, we're working on a powerful computer. So we're doing matrix-matrix multiplies instead of matrix-vector multiplies. So it's big enough that we could do that, but slow enough that basically it runs extremely quickly. So we're going to, always we're going to instantiate our parameters. We're going to initialize them to have some random value, or in the case of a linear model, we can get away even with setting them to have 0 value. And then we're going to pass over our data one mini batch at a time. And for each mini batch, we're going to calculate our function, f of x. We're going to calculate the loss function, right? We're going to take the derivative of the loss function with respect to our parameters, and we're going to scale this by the parameter eta there, which looks kind of like an N with a long second tail. And we're gonna scale it, and then we're gonna use this to update the parameters to take some new value where we hope the objective function is now lower than it, our loss is lower than it was before. Logistic regression has a very similar structure, right? The only difference here is that our output isn't just usually dot product of wx, is that we're also going to run it through what's called a sigmoid function. So we're going to get something like what you have over here, the 1 over 1 plus exponential of, again, we can train this by stochastic gradient descent. Main difference is, right, linear regression is going to be useful when we have a real value target. Logistic regression is valued when we have a classification problem. And again, this familiar kind of ritual of performing stochastic gradient descent is how we're going to optimize it. You can also generalize this to a multi-class case where you basically are now going to have a weight matrix instead of a weight vector. So you're going to have a full set of weights corresponding to every single output that you have. In that case, you're usually going to perform, if it's multi-class, then you're going to have a softmax function instead of a sigmoid function, just to ensure that this is just a function that ensures that the output probability is sum to 1. So if you're saying it's multi-class, then this belongs to one of those categories. You want to be able to interpret your output as a probabilistic prediction. So I think the most instructive thing we could do here now is actually go right back into code and see how all this actually looks. Well, that's a lot of tabs. Yeah? Which one? Cool.
There you go.
Cool. So ultimately, we're going to want to actually implement most of our models sort of taking advantage of the interface features that MXNet confers. But let's just take a quick look at linear regression and show how basically it's quite easy just with ND-array and autograd to implement kind of arbitrary models. And this is quite useful because I think once you know how to do this, especially if you come at it as a researcher, as a modeler, and not as someone who just wants to build something, anything that you want to do that you know how to code with sort of low-level primitives that are defined in Numpy and thus an ND-array, you can build this model whether or not there exists sort of pre-existing support for the particular layer that you want. And knowing how to do everything yourself will make it quite easy to then ultimately define your own layer, even using the abstract interface. So again, these are all the imports we need to do if we wanted to implement linear regression. We just need ND-array and we need autograd. So we can create some sort of fake data set here. So these have already run, right? Yeah, so there. So we can create some fake data set where, say, we're going to have 2 inputs and 1 output. And our model is going to have 3 parameters. We're going to have 1 coefficient corresponding to each of the 2 inputs, plus we're going to have our intercept b. We're going to set some arbitrary number of examples, and we're going to define some kind of real labeling function here to generate labels given our inputs. We'll do this, we'll add a little bit of noise so that it's sort of roughly linear, but with some kind of noise process involved to sort of standard assumption of linear regression. And we can plot our data, so we can see that indeed it does sort of visually, sort of plotting one of our features against the output, appear to have more or less you can visually see that there's a clear linear relationship. So now the way we're going to load up our data is we're going to use what's called a data iterator. So now it's not necessary to use a data iterator, but they do a lot of heavy lifting for you. Sometimes it's quite useful to be familiar with the interface. In this case, we have a data set that has 2 inputs and 10,000 examples. So this could probably fit on a pocket calculator, and you might not know why you need any kind of special machinery. But imagine you were working with, say, now ImageNet, and you say, I have 1 million images, which occupy, I don't remember how big, let's say half a terabyte, and they can't possibly all live in memory at the same time. And I want to be able to use kind of similar code without changing much. So the data iterator interface provides a set of functions that basically you can point it at these what we call like our sort of like serialized large data sets that have been bundled up into what we call rec files, or you could just be passing it a Numpy array, and the same code is going to work. So the important things are, first we're going to define a batch size. The batch size is important because we want to tell the iterator, when I say give me a batch, it knows how many examples to retrieve. We're going to pass it our input x and our label y. It's also not very difficult to create an iterator that does more complicated things. Like if you had a model that took multiple inputs or had multiple outputs, you can also pass in lists. So we're going to tell it the batch size, and we're also going to tell it that we want it to shuffle the data. Shuffling the data just sort of honors the assumption of stochastic gradient descent, which is that actually the samples are selected stochastically. So now you can take a look at how the data iterator actually works. So we can get a new batch just by calling the next method of the data iterator object. So this is going to return us a batch. And the batch has maybe multiple attributes, but 2 we care about especially. We care about the batch.data, and we care about batch.label. And both of these are lists. And the reason why they're lists is because it's possible to define a really complex model that has more than one input or more than one output. So we don't want everything to break and just have to sort of think differently about what kind of objects we're working with in that case. In our case, we actually only have one input, which is our sort of 2-dimensional vector, and we have only one output, which is just a scalar. So you can see if we print data or label. The other thing is to know about a data set is basically we have a data iterator. We want some way of knowing when we've reached the end of an epoch. And when we've reached the end of an epoch, we want to be able to sort of tell it now I want to do another iteration. So the data iterator gives us a reset function. The reset function basically sort of reshuffles the data, right, which you don't have to do after every. Normally, you'll make like one shuffle, and then you'll call the examples in sequence. But once you've made a full pass through the data, you're going to want to reshuffle it. So reset is going to kind of take care of all that machinery under the hood for you. And you can actually call a data iterator as though it's sort of an arbitrary Python list. So things like for batch in train data work. You can even do for like I comma batch in enumerate of train data if you're prefer that kind of iteration loop, or you want to maintain a counter rather than having to write one yourself. So now we're going to do linear regression. So we need, remember we have a 2-dimensional input, 1-dimensional output. So we need to set up some parameters. So our parameters are just going to be ND arrays. And we're going to initialize them randomly, although in this case it doesn't matter. You could just as easily give it zeros and it'll work. And we're going to tell it the shape. So in this case, the shape of our weight is actually going to be 2 by 1 because you only have one output. Our parameter, our bias is just going to be a single scalar 1, which happens to be the number of outputs, right? And we can collect our parameters in an array, which if you're doing things from scratch is kind of useful because then you could do things like iterate through your parameters and for each one attach a gradient. So remember, this is just telling MXNet we're going to want to take a gradient with respect to these guys. These are the only objects in this example where we actually want to take a gradient with respect to them, right? So then actually defining a model, and we can even, right, a linear model is actually a special case of a neural network, is really this simple. We're just going to take some input and calculate our output from it. In case of linear model, it's just a dot product and the addition of the intercept. This example, seems quite simple, but actually, if you understand all the parts of this model, then going from this to implementing a recurrent neural network is not a whole lot of work. All the basic pieces are here, right? We have our data pipeline, we have our parameters, we've indicated that we want to take gradients, we've defined the model. The next thing we need are basically a loss function and an optimizer. So a loss function here is just squared loss, so we're just going to take the difference of y hat and y, and we're going to square it. Something to note is that a loss function in MXNet, you have the option, you can either reduce it to a scalar and return back, say, this is my average loss across all the examples. You can also just return back a list of the losses on each example. That's also acceptable. Basically, the optimizer is quite simple. What we're going to do is, remember, we have our parameters. And once we've called attach grad, we're able to access the gradient with respect to that parameter. We have our W and our B. And for each one, we've called attach grad, which means that they have there exists a W.grad and there exists a B.grad. So basically, once they've been populated, which they will be once we've called backward, we can perform a gradient update by just subtracting from each parameter its gradient scaled by the learning rate. So the only inputs that we need to our optimizer to write one from scratch, you can actually write, most optimizers you can write in not too many lines of code. For SGD, the simplest, right, we just have to iterate through the parameters and subtract their gradients from their values. Something key to note here that I actually skipped over in the NDArray tutorial that's quite important is that you don't want to overwrite the parameter itself. You want to overwrite its value. So the way you can do this in NDArray is you can basically use slice notation. So right, we don't want to have W now points to a completely different NDArray before. What we want to do is an in-place operation where we're going to want to update its current value with its new value. The training loop, to do everything completely yourself from scratch, is actually quite easy. And this is just some bookkeeping code over here, so you don't even have to, even if you didn't look at that, right? Like, this is really the entire training loop that you have to get around. And this is going to look almost identical for every model, no matter how complex. Sometimes, there might be a little bit more bookkeeping that you want to do, or if you have multiple inputs and outputs. But basically, this is almost all this is going to become like kind of a ritual if you do a lot of this sort of work. You're going to set some number of epochs. At the very top of the epoch, you're going to reset your data iterator. In the beginning, this might be kind of a no-op, because it might just be a fresh data iterator. But after each epoch, you'll then want to subsequently reset it. You're going to iterate through the data iterator, so meaning you're going to pass over all the different batches. And for each batch, you're going to say, OK, I want to take the data from the batch. And before I pass it through the model, right, the one thing I'm going to want to do is, so in this case, we're working on CPU, so we don't really care. We don't care where computation takes place, because this model is going to train in seconds. But when we're working on complicated things, we're going to want to be able to say, do this work on the GPU, or do this work on multiple GPUs, or something like that. So we're going to want to have a context parameter that we set in one place. So we're going to remember, we initialize the parameters. They live on the CPU. And we're going to do our computation here. But in subsequent tutorials, we'll prefer to do it on the GPU. So when we get to this point, when we when we grab our data out of the batch, we're going to want to make sure that it lives on the same context as our parameters, the place where we want computation to happen. Right? And usually, the data is going to live on the CPU, and the parameters live on the GPU. So by calling as in context, for those cases where the data doesn't already live on the GPU, this is all you need to do to basically transfer it from one device to the other. So now our data lives on the device of interest. And similarly, we're going to want to pass our label over there. So now you see the sort of typical use case for autograd.record. Right, this is how you use autograd.record. You basically are almost always going to say, I want to record how my output comes from my input, and subsequently how my loss comes from my output. And that's it. Right? This is all you need for the vast majority of models for taking a gradient, is you need to know how does my loss relate to my parameters. And it's related to your parameters through the output as an intermediary and the output through a loss function. And given this, that's enough that you can then just run the code and you have sort of a working linear regression model. I don't know, does anyone have any trouble actually executing the code or following what's going on here? Nope. Yeah? Oh, so this is just like some bookkeeping code I wrote up, like a moving average. So it's just to sort of, if you, typically when you write a training loop, you often want to print out your loss as you're going. And this is a common use, especially when you're testing new code, you want to make sure it works. You want to look at what's happening to the loss as I train. And so if you print out the loss after every single batch, then you can suffer from what I've named batch sickness, which is you just stare at your computer and it's like becomes this like kind of psychotic numerology where you just watch the numbers fluctuate up and down and you're like desperately thinking like, is my whatever it is that you're working on, like my context dependent LSTM or something like actually working? And these models might train over the scope of days. And so you're staring at it and you're like, is it working? Is the loss going down? And it's quite hard to see it because basically what happens is in the very short run, so if you think of time as the number of batches, right? Those time steps, as they're proceeding, in the very short run, what you're seeing more of is variation in the loss over different examples, not variation in the loss over the course of training as a function of having altered your parameters. So what you're often going to want to do is you're going to want to have some kind of like trailing average. So this is just like an exponential decay. So I actually just need to push it live. Actually, I've cleaned up those lines of code to make it a little bit more palatable, so it doesn't dominate so much of the visual in the training loop. But that's really all that's going on here. And we actually have bookkeeping functions that do a lot of this work for you. But I think if you become too dependent on them and you don't know what's actually happening, then that's not a good place to be in. So in the early stages of the interactive book, we've tried to sort of have, in parallel, a sort of completely from scratch version of basic models, and then also how you would do it sort of maybe more commonly in practice using gluon. So for example, we write the evaluation metric ourselves when we do it, but we maybe will use MXNet bookkeeping in the gluon version. And then maybe after the first few chapters, first few parts of the book, we'll kind of basically say, oh, now that you know gluon, we can teach more advanced models and take for granted that you know how to do these things and don't write them yourself. Yeah?
What happens if you do something undifferentiable instead of autograd?
Well, then you can't take a derivative. It depends. I mean, you can have things like you can have randomness that's incorporated into your model, but like your output has to be differentiable with respect to, say, the parameter, or the loss has to be differentiable with respect to the parameter. Now, it's okay if your function on each pass can, there could be aspects of your model that are not necessarily themselves differentiable. Like the actual, and not to go like too far into the weeds, but for example, I don't know if you're familiar with these like recursive neural networks that build a tree structure and they combine the representations of two nodes to form like a new internal node. And the actual, in that work, I think made famous by Richard Socher and Andrew Ng, there's some kind of like logic that determines what the tree structure will be on each pass based on the distance of certain representations to each other based on the magnitude of a reconstruction error or something funny. I don't want to go too far off, but you get the point. That part of what's happening is not differentiable. That's fine. It's OK to have non-differentiable functions that are used to build the graph, but ultimately you wind up with a computation where I have a loss and I have some parameters, and the exact values that are in the loss right now, like the actual arithmetic that was done to compute them, depended upon differentiable operations. And in that setting, well, obviously, you can then still take the derivative just by calling backwards. What you can't do is say, like, OK, I'm going to have my model all the way up to y, and then I'm going to have z, which doesn't depend in any way on y, and then my loss, which depends on z. Well, you can't take a derivative of z with respect to a function that was used to compute y, because z actually doesn't depend on y. There is no derivative. It doesn't actually exist. Any other questions? Yeah?
I have a question from your code. Why do you take on the first element of batch data and batch label?
Yeah, so linear regression is quite a simple case. It's sort of, I have one input and one output, right? There's all kinds of other training schemes that you might encounter in machine learning where you're going to say, I want to have multiple inputs and multiple outputs, for example. Here's a single paper that comes to mind. I have a friend, Melody, had a paper on crowdsourcing, and they had an idea of telling the model, conditioning the model on the identity of a crowd worker. So the label is a label that was annotated by a human, and different humans might have different biases, so you want to actually model the difference in the humans. So in this case, say you're doing image classification, so you're looking at medical images, you have two inputs. You have one is, what is the identity of the crowd worker who did the annotation? Or in this case, maybe it was actually like, wasn't Mechanical Turk, but it was maybe like a professional radiologist who was labeling an X-ray or something. But it's like, what is the identity of the worker? And what is the actual image itself? You need to pass both of these into the model in order to calculate your output and then calculate your loss, right? Similarly, you might also have multiple outputs. So you might have a model that does something funny like, it's actually quite common, like some kind of multitask learning. Like you might say, hey, I have a model and I want it to predict one thing. So I want it to give me softmax output that should match against categorical label. So what's a good example of this? Say I'm working in recommender systems. So I've done some of this work with Julian Macaulay where he's got these things where sort of like most classic recommender system tasks maybe is something like rating prediction. Like I want to predict the rating, like say 5 stars. So you'll pretend it's a sort of like real valued regression problem, even though it's kind of discrete. And you say, I want to predict a rating given this user and this item. But then you might simultaneously say something like, I also want to regularize this model by generating the product review that this user might write about this item. So now you have this like input, which is you have two inputs, a user and an item, and you have two outputs, a rating, which is a real valued score, and then actually a text string whose probability you're trying to maximize using some recurrent neural network, some exotic model. You get the idea that not every model has multiple inputs, not every model has multiple outputs. But many models do, and you don't want to have to do something drastically different if you find yourself in such a case. So basically, by having your batch.data be a list and your batch.label be a list, it's easy to access the appropriate element. Everyone good? Cool. So probably the most suitable next thing is to see how we would do this maybe more succinctly in gluon. What's going on here? Alex, huh?
We're back. Okay, so let's do something, very simple and some speeding up things a little bit because we are running a little bit behind schedule. By the way, if you find it hard to read things in the back, there's a very easy way how you can zoom in. There are seats in front. So sorry for being maybe not very, being very diplomatic here, but the problem is simply that if I zoom in here, then you won't be able to read the code anymore later, right? And it's still not going to be good enough. So I can try that a little bit, but it's not going to help you because it'll just horribly wrap around. Okay, so let's get started, right? So what we just saw was a very simple setup for where we define every single piece of the model by hand, right? So we define the function class, the loss function, everything by hand. Now what I'm going to do is I'm going to do the very same thing, but just using gluon components. Okay, so let's step through it. And the first thing, of course, is the usual import ritual. And we are basically importing MXNet and the array autograd and gluon. Okay, fine. The next thing that we're going to do is, this is actually now going to run on a GPU. This is why we're doing everything remote, because I don't have a GPU in there. And now let's pick a data set that's a little bit less toyish. So it's still a toy data set, the MNIST data set, right? And what I've basically done here is created iterators, which just like before on the toy data set, now for MNIST, will give me one or multiple observations at a time. If you have a weird data source, you will probably have to write your own iterator. But for most sensible data sources, there's probably an iterator that will do what you need. So for most places where you can store things, anywhere from S3 to HDFS, we have routines. For most data types, we have routines. If you have something weird, you probably have to write your own iterator, but that's not very hard. And there's actually a notebook that describes that, for instance, for text. Okay, fine. Pardon? There's a JSON format iterator, yes. But then you still need to make sure that whatever you ingest from JSON is actually usefully used later, right? So it's kind of hard for me off the top of my head to confirm that the existing iterators will work for your data set, but there's plenty of iterators there, and this is open source. So if you write one, please do us the favor of contributing it back, because that way chances are somebody else will be very grateful to you. This is why it's an Apache project. The interesting thing here is we have two iterators, one for the training set, one for the test set, and of course you can rewind and reset and whatever. Fine. So now let's go and define our network. So we basically decided, okay, let's have 256 hidden units, and we define a network called NN sequential. That's just gluon neural network sequential concatenation of pieces. I could also have just done this explicitly, but in this case it's a little bit easier to just say add a layer, add a layer, add a layer, right? Now, one fairly interesting thing that you may notice here is, okay, so the activation is already part of that layer call. That's what I meant also before with you can actually fuse several pieces together. The other part is there is no description of the input size. So I'm just defining a neural network with 256 hidden units without specifying the input. The reason why I don't have to do that is because later on, when it's executed the first time, it actually will find out what the size is. So it does automatic size inference. This is kind of boring for an MLP where everybody can straightforwardly figure out what the sizes are. But once you're down to the 20th convolution in your ConvNet and you're stacking things together and so on, this is a wonderful source of errors, right? By automatic size inference, you will not encounter those errors, right? It just makes your life less painful. Okay, fine. So now the next thing that I'm going to do is I'm going to initialize the parameters, which is a weird thing because I'm initializing parameters that don't exist yet. So how can I do this? Well, and by the way, there are tons of different initializations, uniform ones, Xavier and Gaussians and zeros and ones and whatever you wish, and you can do that on a per layer specific basis. The reason why I can do this is because it basically performs this in a lazy deferred update. Right? So it will not do it until it actually knows what the parameters are. A little detail here. So you see this thing called CTX equals CTX. CTX is the device context, and in this case, I set the device context to a GPU. Actually, there are 2 GPUs on it. If I call it without an argument, it'll just pick GPU 1. But I could have picked, some other one. And we'll see multi-GPU code later, but that requires a few more lines of code, and I don't want to obfuscate it. OK, fine. We need a loss function, and we need an optimizer. So this is an SGD solver, right? And I'm just picking a fixed learning rate, 0.1 here. This is actually a little bit smarter than just a plain dumb stochastic gradient descent optimizer. It does it does a couple of useful things. It does, for instance, gradient clipping. So if the gradient is larger than some sensible number, it'll truncate it to that. This is good for a number of reasons. For instance, if you have some GPU at home and it's overheating, it may actually give you very large random gradients. This is not a myth. This will actually happen to you if you build your box at home. It shouldn't happen on AWS GPUs, but if you have some GPUs at home, it can happen. As in, I've built such boxes, unfortunately. The second thing is, it doesn't just do SGD. It actually uses momentum and a few other things. So this is not a bad solver as a default. The only thing that you should set is the learning rate, and you may actually want to adjust it on large runs to keep it constant and decrease and decrease. You can turn the momentum term off and all of that by just changing those command line arguments. We're not going to bother about that here. Okay. So basically, by default, most of those things are set sensibly. There are 11 different optimizers in MXNet right now. It's about 20 lines of code to add a new one. Most likely, the one that you want is in there. If you have desires for some other exotic optimizer, yeah, it's 20 lines of code. That should be easy. Evaluation metric, that's, again, the bookkeeping. And I'm not going to go into a lot of details here because that's kind of boring. Now, here's where the interesting things happen. And let me just start it before I discuss what we're seeing here. So this is 10 iterations. And it just goes through it 10 times. Every time we start looking through the training data, we reset the iterations. Okay, that's kind of a sane thing to do, right? Otherwise, you go through the data in the same way again. And we already specified before that, reshuffle. Okay. So then we go through the data in batches because, well, we specified a mini batch size before. And so we get data and labels because that's what our iterator gives us. Okay, so this is completely standard as before, except that now we are using all the nice gluon infrastructure. And then the actual training loop is exactly the same as what you would have seen before. We start recording the gradient with autograd record. Okay, compute the output, which is some network of data, which is basically what the network would predict. So if you wanted to do only inference, you would not use autograd record. So this way, it would not actually record and store all of that and just give you the output. You then need to score how well you're doing. So that's loss equals softmax cross entropy of output and label. I could have called it something a little bit shorter, just like loss. And then lost or backward does the backprop. And actually, this is a bug. It should be here. Well, why should lost or backward not be in the autograd record? Well, for a very simple reason, because the backprop step itself doesn't need to be recorded, right? This is essentially applying the backprop step to the computer graph. It still runs, otherwise gives you the same results. It's just a bit slower. Now, trainer step then does nothing else but just does an update step on that loss.
Alex,
Yes?
can you talk a little bit about just the mechanics of what's going on within that autograd there? Like the
Okay.
output and the loss, and
Yep.
just what's happening with those 5 lines starting
Okay, so autograd record basically turns on essentially internal. Okay, so first of all, we had to attach gradients to some variables, right, to the parameters, right? This happened implicitly up here when we defined the network. So this is one of the nice things if you define the network this way, that the gradient attachment is automatically done to the parameters. So you basically, because you need to tell MXNet, hey, by the way, these are the variables that I want to optimize over. So rather than a neural network, you could use some other, you could use some controller with parameters. Doesn't really matter, right? Or, some, physics experiment where maybe you want to compute the resistance of, a resistor, right? But you then need to tell it, hey, this is the parameter over which I want to optimize. And this is a little bit hidden insofar as it basically automatically attaches the gradients here. So now, as I start with autograd record, it basically, now in the next two steps, it records whatever programs are being executed there. And the pieces that it records are basically all the pieces where the variables that you care about, and this is in this case the loss, right? So it basically looks for all the variables, what you need to record. And now for these variables, it will then afterwards give you the sensitivity analysis back, right? So in that sense, it's a fairly expensive operation that's being carried out here, right? Because you basically need to keep all the intermediate steps, all the intermediate values around, and then only when you say, lost or backward, will it go and work back from loss to, what depended on the input variables. And it'll basically run the backprop there. Now, this is very expensive, so this is why a JIT compiler will help you quite a bit, and we'll talk about that JIT compiler a bit later. Now then, trainer step does nothing else but just, pick this gradient and does an update step. That's very straightforward. And the rest is bookkeeping. There's nothing particularly magic going on here. Now let's actually see what happened. And yeah, basically what you see is that on MNIST, a two-layer, multi-layer perceptron produces an error of about, 2.4% or 2.3 something percent. That's mediocre for MNIST. You can do a lot better. But it's pretty decent for a simple attempt, right? And the point here was not to do better, right? Okay, now this, yes?
How do I know if I need to determine the parameters that I'm taking the gradient with respect to explicitly, or is it implicit?
Well, you basically need to tell MXNet what the objective is that you want to minimize, right? Right, so it's a loss function or something. I mean, how else would MXNet know, what you want to optimize over?
Sure,
right?
That I understand, but I'm asking, in previous examples, we explicitly said, use this.
Yes.
But here we didn't.
No, we did. So this is, okay, so maybe I didn't explain it terribly well. So loss or backward, this is where we are telling MXNet, hey, by the way, it's the loss that we want to minimize, right? And backward now calls exactly, computes the gradient with regard to the parameters that I before that attached the gradient to.
That's what I'm asking.
Right.
Because we didn't explicitly
Yeah.
attach, right?
So so this is what happens up here. That's this marked up piece. So when you define the network, it does amongst other things the convenient thing of already attaching gradients to it, right?
And that's because I'm using nn.sequential?
No, because you're using with net name scope, right? So with that, part, you are basically essentially using Python magic to make this happen, right? You could also just, explicitly calculate it and then, go through all the parameters. So parameter collect, attach gradient. You could do that explicitly. So like with most things here, it's batteries included but removable, so you can take pieces apart to quite some extent. but I wanted to show you the fancy, convenient version where everything is fairly automatic. And before that, Zach showed you the brute force Stone Age bare bones version where you construct everything by hand. And everybody will probably have a slightly different style of how they code. What happens behind the scenes is very similar. Yes?
May I call loss backward without calling autograd report?
You could call it, but it'll produce an error. And so the reason is basically, unless you've actually recorded, the computational graph, right? Dot backward will not know, what it needs to compute, the gradient of, right? So it's because there's no graph attached, right? So it's like, let's say we have some function f of x, right? And let's say f of x is 5. If I just tell you 5 and give me the gradient of, it's not going to work. So in order to know that it's the function f of x, I need to, record how I arrived at the function value 5 by starting with x. So x attached gradients will tell MXNet that, okay, I care about the gradients with regard to x. And f.backward will then, tell me that I need to work my way back from f. So later on, when we look at generative adversarial networks, we'll actually get a situation where we have two sets of variables and two functions, and they're within one nested optimization loop, because we have basically a generative and an adversarial network. And the reason why we're going to go through that in detail is to make it explicit how you can have multiple functions, multiple sets of parameters, multiple gradients, and them all interacting. So doing that is fairly straightforward here. This would be a lot harder in a symbolic framework, right? Because here you can just write the code as you wish it. Yep. So let's move on to loss functions, because we're running a little bit behind time. So we already talked about least mean squares, and I guess everybody knows that one, right? And here's just the loss and the gradient. This is actually plotted using MXNet, because I was too lazy to do it otherwise. So what I simply did is I defined a loss function L2, and then I actually ran the gradient backward. Actually, let me show you how this looks like. So I didn't actually even have to go and explicitly compute this loss, this orange curve. This kind of makes life easier. Okay, there we go. Okay, import ritual. Actually, we started with an L1 loss here. Okay, so, and because I'm being lazy, I'm actually just using the gluon L1 loss. Somebody coded that up already. And so what I did is I compute an output. So that's basically that's actually the input to the loss, but it's basically just values between -5 and 5. I now say, well, I want to get the gradients with regard to this because I need to get, the dx. Then the label in this case, would be zeros, because I want to, look at the difference between, let's say 3 and 0 and get that gradient. And then now just with autograd record, I just compute the loss, which is now the loss between the output and the labels, and I compute the backprop, right? So I've now, for the entire graph, computed the derivative everywhere. So it's really, really simple. And then I'm just plotting it. So let's see what happens. And we can see that what we get is exactly what we would expect. This is the L1 loss, right? It's just the absolute value. And then here the green line, that if you squint at it, is the derivative. Okay, let's try that for something else like L2. And for L2, it's the same thing. We basically just have the L2 loss here, and that's its derivative, right? And okay, so this is fairly boring. Now let's get to something more interesting. Who's heard of Huber's robust loss before? Okay. Who's heard of a trimmed mean estimator? I think all hands will go up. Oh, no. So trimmed mean estimators are something that's really useful in robust statistics, and they date back to the Middle Ages. So if you've spent some time in the United States, you would have heard of the definition of 1 foot, right? Trouble is, my foot is maybe smaller than your foot or maybe bigger than somebody else's foot. So how would you in the Middle Ages define 1 foot in a reasonably portable way, right? Because you can't just, cut off a foot and take it to every village. So here was the prescription for how to calculate 1 foot. It said, take the first 12 men who walk out of church because that's the place where everybody goes on Sunday in the Middle Ages, right? Because otherwise you are in hell and whatever, right? And so you take the first 12 men, you send away the 2 men with the longest foot. You send away the 2 cripples with the shortest feet. You take the remaining 8 men, you have them line up basically heel to toe in one line. You divide that by 8, hence you start with 12 because division by 2 is really easy to do. You divide that by 8 and you have 1 foot. Now what this did is it was basically a robust estimator of foot length. Why would you send away the 2 guys with the shortest feet? Because, well, Middle Ages, feet get maimed and wars and stuff. Likewise, longest feet, same reason, anomalies and so on, right? Orthopedic surgery wasn't very good during that time. So the result of that is basically you take the average of something where you remove the outliers. It took until about the 50s or 60s that Peter Huber came up with a more mathematical definition of that, which is basically take the gradients of the loss function and clip it at the extremes. Basically, clip this, the gradient there. Now, what I've done is here in this little piece of code, Huber, I've basically done that exactly for the L2 loss. And there's a little bit more description in the notebook that explains a little bit how the math works and so on. But basically what I've done is I've first of all computed the absolute value. Actually, let's draw that function for a moment. It's basically linear outside some range. And it's, quadratic in the middle. And then it's pieced together in such a way that it's a smooth derivative. Okay, so that's the function, right? So basically loss, and because I didn't want to explicitly use if then else because I like to vectorize my expressions, it's just loss greater than rho times loss minus rho over 2 plus 1/2 over rho times loss less equal than rho then times loss squared. So if you work it out, this is basically a nice cases statement where it's linear on the outside and quadratic in the middle. So here's the math that goes with it. In any case, then I was too lazy to compute the gradient explicitly. And I just, again, do the following thing. The loss is the loss between output and then ND zeros like output. This is a really useful thing, zeros like or ones like. It basically produces another vector that has exactly the same shape as what you feed in, but it's all zeros or all ones. In some cases, you need stuff like this. And then you just call the loss stop backward, which is now going to compute the derivative everywhere on that graph. And so we plot it. And lo and behold, this is exactly what we get. So we get linear here, quadratic there. And then we have basically clipped gradients on both ends and linear in the middle. So this is another example of a loss function where you can, very simply procedurally define it and then everything works. And I could now throw that at the solver, right? So if I don't like the losses that are in, gluon, well, 5 lines of Python will happily give me a robust loss. And this is all Git clonable, obviously, so it's very easy. Fine, so since we've done that, we can skip through that very quickly. All right, that's exactly the loss that I talked about, and I literally cut and pasted from the notebook. There's also something called a logistic loss, and that's basically if you want to map things, from, R to maybe numbers between 0 and 1. And it's basically, softmax to distinguish between two classes. So P of y given f is 1 over 1 plus e to the minus yf. You may want to do interesting things in terms of, numerical stability for calculation, but this is the math. And again, produced in the same way. And of course, the blue and the green curve are just for, positive and negative classes, right? That's the loss, of course, the negative log likelihood there. Multinomial logistic loss, this is basis of max that we talked about before. It's, minus log of P of y given f, and that's, the softmax minus fy. And you could just code it up this way, or what you would probably want to do if you want to do it for real, the gradient of that, there are numerically stable ways of computing it. Do not program it the way I've written it. This is a big warning, because actually, if you do that, and in some of the notebooks from scratch we've done it this way, you will actually get NANs. The reason being that if you have some largish number, and if you exponentiate it, some really bad things can happen to you, and the log may not save you because this may have already become infinity, so log of infinity becomes garbage. But we all know how to fix this, right? You just take the maximum of the vector for which you want to compute the softmax, pull that out right up front and subtract it. So this is minor details. That's exactly why you want to use a framework like gluon, for instance, to take care of all those pitfalls for you, such that you don't have to, right? Because it's kind of boring having to worry about that every time. So we did the loss functions. So now let's actually look at convnets. So let's intersperse a little bit of basically math again, a bit of theory. So we all know the game Where's Waldo, right? This is perennial excitement for kids. Find Waldo in a picture. In this case, it's super easy. But what's really interesting here about this is that, the Waldo model is global. In other words, the Waldo-ness doesn't depend on where in the image it is. And, if you have those children's books and you need to play Where's Waldo, well, the point is we know exactly what Waldo looks like, and it doesn't matter where in the image he might be. It's always the same Waldo we need to find. The second thing is that the Waldo-ness itself is fairly local. Usually it's some small figure somewhere. And whatever happens in the rest of the image doesn't really have a lot of bearing on where Waldo occurs. Now, okay, that's kind of a silly example, but overall, a lot of object recognition works this way. And this is actually what forms the basis of convolutional networks. So the idea is basically that, and this is more mathy speak now, is that images have some translation invariance, at least to some extent. And that, lower level, it's mostly edge detection and usually via convolution. But here's actually how you can get from a standard multilayer perceptron to a convnet straight away. So if you think about it, a multilayer perceptron on a megapixel image would be maybe, 1 million by, whatever number of dimensions that you want to have as your output parameters. Let's say we go to, 1,000 parameters, which is, not unreasonable. So then it's 1 billion parameters. And we all know that we don't have 1 billion images for training data, so this is mission impossible and it's stupid, right? Because you probably want to have multiple of those layers. However, we also know that the relevant information only is found in, some relevant neighborhood of a pixel. So if this is my weight matrix, Wij, AB, right? This is now just, Ij and AB are the coordinates for the input and the output, and Xij is basically the original image, right? Then I know that I really only need to look in a range, A and B, which is close to the pixel that I care about in this case. So therefore, the sum doesn't go over the entire image anymore, but just from minus delta to plus delta in both directions, right? So that already reduces the dimensionality a lot. So this gives us essentially a multilayer perceptron that is now local, but still not translation invariant. I could have different filters here, from there, from there, from there. Now, to make this entire thing translation invariant, all I do is I basically just go and drop the first 2 indices here. And this essentially drops, the dimensionality for a megapixel image by 1,000,000, right? Because I'm basically throwing away 1,000,000 indices here, right? And so now we have our convolutional mask times this, which is exactly a convnet. So if you didn't know about convnets and just used those 2 conditions, you derive a convnets again, which is pretty cool. Now, of course, Jan LeCun did that, about 22, 23 years ago with LeNet. But there are other cases where you have similar constraints where you can probably custom engineer your neural network for your specific application right now. And of course, this gives you something like, LeNet. So here's one minor detail. So there's this thing called, pooling. And now why do I need pooling? Well, because I might want to have more than one of those masks, right? Why? Because I can, because each convolutional patch may be 5 by 5, doesn't require a lot of parameters, right? 5 by 5 is 25 numbers. So I've reduced it from 1 billion numbers to 25. So hey, let's just take 100 of those, right? It's still small. So I get many of those feature masks, right? But then I need to reduce the dimensionality because otherwise even a simple, MNIST image will become quite monstrous. So I just downres everything. And that's the average pooling, right? That's what you would do usually for downresing. Now, what works a little bit better is something called max pooling, where you take, let's say, 4 pixels and you just take the maximum over them. And then you convolve again, and then you downres again, and you do that a few times. And in the end, you throw a couple of dense layers at it. And that's LeNet. And that's LeNet in gluon, right? Well, if Jan LeCun had that in 95, then, it would have probably taken him less than a year to build this. Of course, that's totally cheating because we're relying on so much more software technology and other pieces there. But basically, the reason why I'm showing you this is because this stuff is now simple enough that your laptop can do it in a few minutes. Right? This is, at the time, this was running on some fairly high-end SGI Octane workstation that, was basically nice and purplish and fridge-sized. So I saw the machines at the time because I was the intern. Anyway, the interesting part here really is, again, that size and shape inference is automatic. So there's no definition where I say, well, the input images are 20 by 20 pixels or 28 by 28. Just a few more layers, and then we'll walk through that in detail. Well, we have all the usual layers, right? So we have dense and activations and dropout and batch norms and embeddings and convolutions and pooling layers. So anything that you would expect, any framework to have, we have that obviously because, we would. So let's look at that in a bit more detail. Here's our convolutional network. Okay, so let's just import that. And we put that onto GPU 0. And we get the MNIST dataset again. This is exactly as before. Now let's actually define the network. So this is just what I walked you through before. So there's a convolution. And I cheat a little bit because it's not really LeNet, right? This is basically max pooling rather than average pooling. And I'm using ReLU rather than sigmoids. But you could, for nostalgia's sake, use sigmoids, but it would work slightly worse. So that's why I'm not going to bother. There's an interesting operation here. There are a couple of interesting operations, right? So channels and kernel size. So kernel size is basically the size of the convolution. 5 by 5 is kind of, a sensible number. Channels, that means how many filters. Now, channels in and channels out means you're actually doing a matrix vector multiplication on the channels dimensions and the convolution on the image dimensions, right? So you're using all the input channels and that patch. So it's actually a little bit more powerful than just a simple convolution. And then here's an important thing, because we are still dealing with basically a stack of images. So this is actually a three-dimensional tensor now, really, because you have, one dimension for all the channels, one dimension for the x, one dimension for the y's. And so now in the end, before we run that through a multi-layer perceptron, we just need to flatten this. And this basically squishes out all dimensions and just turns it into one ginormous vector. And then, okay, we run that through a fully connected layer, right, FC512, just because. And then in the end, just turn it into number of outputs. So there's nothing particularly surprising in there. Any questions about it? Nothing really particularly exciting. Okay, so then finally we initialize our parameters. And by the way, at this flattened point, if I had to do manual size inference, it would be painful, right? Because you'd have to keep track of how many parameters do I really have after all of this. I would bet that most people, including me, would screw this up. Okay, now we have a simple loss function. Okay, fine. We have our optimizer again. We have our accuracy evaluator, which is exactly the same as before. And now we train. And so let's look at the training loop again. It looks exactly the same as what we saw before. As in, you can use literally the same one. The only thing that changed here was our network definition, right? So it's again with autograd record. Output is net of data. Loss, okay, well, again, cross entropy loss, and then backprop, an update. So this is exactly the same. You could implement your own optimizer, no problem. And then, yeah, it's basically starting to produce numbers at some reasonable speed. And you can see this is actually working a bit better now than before when we had, a multi-layer perceptron, which isn't totally surprising because, well, this is, a better network architecture. So now let me get to something while this is running that's actually pretty cool. Hybridization. So hybridization, so we sort of kind of hinted at it a few times, is basically where you take the compute graph. So in TensorFlow, you explicitly construct a compute graph and you say compile and run, right? Likewise in Keras and in Caffe, it's kind of a bit strange, but in Caffe 1, you have basically that proto file, and then Caffe does its thing and optimizes over it. Here, we implicitly define it by, writing some piece of code. And of course, if, we don't tell MXNet that that graph is going to stay around for a while, then poor MXNet has no alternative than to just compute it over and over and over again. And that's very computationally inefficient. So that's why there's a JIT compiler, and okay, in MXNet it's called hybridization. So let's just start that from scratch here. So what we're doing here is, well, we're just first actually constructing some network, right? And there's actually another interesting thing about this here. We have a function that returns a network, which is kind of nice. So because, in Python, variables are functions, you can just call it, getNet, and it'll return you a network back, and you can actually use that to compose larger networks, and we'll see that later. Okay, fine. So I, get some network, and then, I can just, print the output for some random input, right? So I'm taking, 512-dimensional input, and I get 2-dimensional outputs, and yeah, whatever, fine. That's what I get. Now, what I can do now is I can, run hybridize. And that's kind of, okay, nothing really interesting happens. I mean, it gives me exactly the same output as before, as it should. Now, in general, in case of doubt, pick hybrid sequential as opposed to sequential, and always call net.hybridize. So what does hybridize really do? So let's actually benchmark a little bit what happens. So so my benchmark code is very primitive. It basically runs something 1,000 times. So let's run this. And what we can see is that before hybridizing, it takes 0.35 seconds, and after hybridization, it takes 0.21 seconds. And those numbers are bound to decrease rather drastically over the next month as we improve some pieces of that JIT compiler. Right? So, okay, this is good. So I do something that's trivial, and my code goes faster. But what happens really? So the first thing is, let's actually look at what the program is that we are getting. So what I'm doing is I'm producing, first of all, some symbolic variable. Okay. So as opposed to feeding real data through the network, I'm now feeding a symbol through that network. Okay, it's kind of weird, right? So what that does is it basically generates now as an output no longer a number, but it now generates the compute graph as the output. Because the symbol basically traces through all the steps that are happening, and now the answer is no longer the number, but actually the recipe how to produce a number, right? And let's have a look at what happens. So, the input is just some symbol. The symbolic part of that net is just, okay, that's hybrid sequential. Okay, that doesn't really help me very much. But what I can now do is I can export that thing to JSON. And so now here's some very long and fairly human unreadable network definition of each of the steps in the computational graph that are being executed. Meh, okay, that's kind of boring. Why would I care? Let's say you want to use this and export it, for instance, to CoreML. Or you export it to Caffe, or you export it to something else that's not MXNet. Or you want to export it to some embedded system and some compute device. Well, you actually need to export the network definition, right? This is how you export it. And then, you convert it to Qualcomm Snappy or to, Apple's CoreML or to anything like that, and you run it on those devices. So you do all the work efficiently on MXNet, and then in the end, you just dump it out. Okay. And so if I wanted to do that, all I needed to do is just y.save will just save the model. And net.save will save the parameters. That's it. This is how you serialize all the network weights. Okay, it's kind of nice. Yes?
Does MXNet have something like TensorBoard, or do I have to just use this JSON to visualize it?
It has TensorBoard. So, so there's currently a slightly delicate situation. So, okay, so I'm not sure how to put this delicately enough. So Google's done an awesome job with TensorBoard. And a lot of pieces in TensorBoard don't need TensorFlow. So some kind soul, I think at Alibaba, went and liberated TensorBoard to make it accessible to a large number of other deep learning frameworks. And they've maintained this patch. And MXNet also uses this. At some point, Google decided that they had their own plans of how they would treat the open source release of TensorBoard. And they are currently struggling with accepting those patches for some reasons that I probably don't fully understand. And they wrote the code, and they are the copyright holders of TensorBoard. And if you look on GitHub, you can see the full conversation between essentially the original TensorBoard authors and the people who extended the functionality, and you can basically draw your own conclusions. I can only tell you that in MXNet's case, we're on Apache, so we do not constrain how you use our software. Right, so this is Apache Incubator MXNet for good reason, to exactly give that kind of confidence. What will happen to TensorBoard, I do not know, but it's supported in MXNet, and maybe at the next tutorial we can go through this in a bit more detail. But yes, you can run it. So this is just right now a little bit delicate. Okay, fine. So just to get to the last part, namely hybrid blocks. So blocks are basically layers, but we call it blocks because you can stack multiple layers together and you get another meta layer, and rather than calling it a meta layer, everything's just a block. And that's it. So blocks are a way of how you can make the functional dependence a little bit easier to understand. So remember, before that, we defined our network by just saying, well, with network, add a layer, add a layer, add a layer, right? What you can also do is you can first say, by the way, I would like to have those components in my network, right? A fully connected layer that's dense with 256, one with 128, and one with 2 dimensions, right? I can do that. And then I say, well, actually, here's how my forward pass in that network should look like. First, actually go and print something out. Well, because, hey, why not? Then x is, some function of relu, which is now applied to, the fully connected layer. Then there's another fully connected layer, and then, return whatever comes out of that. So this is now a piece of code. You could have control flow if then else in there. That's fine. Okay. So this is basically an alternative way of writing the same network as what we had before. Okay. Now let's actually do this. And every time we call it, it basically just spits out x is an ND array and f is the MXNet ND array context. So now let's run it again after we hybridize. Okay. And something very strange happens, right? And basically, after the second forward pass, it no longer prints anything. It's weird, right? So it's the same piece of code, but I just called hybridize, and the first time it printed stuff, the second time it didn't print stuff. So here's what happened. Basically, hybridize tells MXNet to now go and record this path and assume that it's fixed until I call hybridize again, of course. Right? And so now it records the computational graph and it caches it. So the second time I invoke the same function, it doesn't actually execute the function code anymore, the Python code, but it just uses the computational graph that it's cached. So this is how you can get essentially symbolic framework-like speed with an imperative framework, right? And if you think about it, right, you maybe run stuff on ImageNet, and maybe you have, a million evaluations of that network. It's completely negligible how much time you spend on the first of these 1 million evaluations. You basically pay the price once for the first evaluation, you compute the computational graph, and then for all the remaining 1 million minus 1 steps, you get the compiled speed. That's basically what's going on behind the scenes. Okay? And that's all that there is about the JIT compiler. So let's just go back to a few more slides. We probably won't get through all of the ConfNet part before lunch, but let's just talk a little bit about fancy structures and how to compose stuff. Because the networks that I showed you so far, they're very much 1990s. So let's move on to the current decade. And so one really big insight was in the Inception paper, where they took multiple convolutions and just tried them out in parallel, right? If you look at that, right, I mean, this is one of those blocks. You have a 1-by-1 convolution, which is basically just matrix multiplication within one pixel, but all the filters, 3-by-3, 5-by-5, and 3-by-3 max pooling. And you might argue, which one of those things is really the best thing? Well, let's just try them all out, right? Or you have one of those, and maybe you have some of these, and you can come up with much fancier structure. But basically, what you now do is you have one building block as, they call it, I think, an inception block, and you can stack several of them together. And if you do that, then maybe you end up with 100, 200, 300 different layers. And building such a thing by hand, as in, in code, is extremely horrible, right? Because that's really what you get, right? So now the good thing is this is code. So I can write a little piece of computer code that will go through this, right? Because we have the regularity in there. It's just like if you count from 1 to 10, you don't write out the numbers from 1 to 10, but you write a for loop. In the same way, we do that here. So now let me explain how this works. So hybrid sequential is exactly the piece where you, for instance, piece together a convolution and then a batch normalization, and we'll get to exactly what the batch normalization is. It's, for now, just assume it's one of those layers. And then an activation. Right? That's now one block. It's 3 individual blocks. This is really like playing Lego. The only difference is I can now invoke it many times, and the only time that I have to spend any effort is to write out those 6 lines of code. So now, let's say I want to compose multiple of those blocks into one branch. Well, all I need to do is I just, fine, we just, do the hybrid sequential again. So this is a function that returns a network as an argument. And it just adds, first it does, some max pooling. So first of all, it does this hybrid sequential, right? Okay, this is basically where we are going to put everything in. It max pools. And now it basically adds multiple basic blocks. Right? So this is basically just now a for loop, which, for different numbers of channels and other parameters, just keeps on happily, cheerfully adding one block after the other. So we get this. This is one block. Now we have, for instance, 3. Okay. So now, let's say we want to have not just one, but we have one branch with 3, one with 2, one with 1, one with 1 there. Okay, fine. So what you need is, rather than a sequential composition, you need a parallel composition, right? And that's called hybrid concurrent or hybrid parallel, right? Basically just does a parallel composition. So this is really just how you would build a graph. So in this case, we're basically taking advantage of the fact that, yes, you can do stuff that look very much like a symbolic framework. It's called MXNet for a reason. MxNet, because you can mix things together whichever way you want. And the other thing that you see here is that each of those branches themselves are functions that will give me a suitably parameterized network. And so the entire network is actually fairly painless to write out. And let's actually look at that in some code. And given that it's 8 minutes to lunchtime, we probably won't have much time to run this. Okay. So we're just going to scroll through it. So this is basically, we import a network. There's some data transformers, data loaders. Just usual boring stuff. I'm not going to go into this. But this is now exactly where things get interesting. So we have one VGG block, right? That block basically just is a sequence of convolutions, and in the end, it does a max pooling. There's a for loop for number of convolutions for the suitable number of channels. Keep on convolving, in the end, max pool. Now, if I want to have multiple of those, one after the other, all I do is, so the architecture, and this is actually the entire variable architecture, it tells me that I, for instance, want to have 2 blocks of this type with that width, 2 blocks with that width, and 3 with that, and so on and so on. Basically goes through that and stacks them up one after the other. Right? And so then in the end, I basically go and flatten things. And that's it. So let me actually do something that's a little bit less horrific for our poor GPU. And then after I've basically built that entire stack. So this is 17 layers of network. And since this function call gave me a network, now I add it to something else, and I keep on stacking things together. In the end, well, fine, I have some dense layers, and then I'm done. So in the end, of course, you make the obligatory hybridize call, because you like speed, right? So this can give you up to twice the speed. You initialize, you use the optimizer as you would, and everything else is really boring because it looks exactly the same as before. Right. So one piece of warning here, you do not want to have a large mini batch when you run a VGG, because it's quite monstrous in terms of network size, because otherwise you get this, where it complains out of memory. CUDA malloc failed. What happens is basically, if you think about it, we have those very dense MLPs. And so, 4,000 by 4,000 matrix is a big matrix, right? And backpropping through that and, allocating that is kind of painful. And that's why, things can actually go south, unless you use smaller data types. But the 4,000 by 4,000 matrix, right, that's basically, 16 million parameters, and then, times number of batches and so on. This gets painful. Okay. And with that, I would say we've all deserved a lunch break. We'll reconvene at 1:30. And there'll be 2 more hours. So what we'll do after the lunch break is, after batch normalization and other things, basically optimization. And then we'll talk about generative adversarial networks. So that'll show you how to have multiple loss functions, multiple gradients and variables. Then we'll talk about LSTMs, tree LSTMs, which is one of the places where, dynamic structures really matter. And in the end, we'll talk a little bit about infrastructure on AWS, parallel training, and how you do that with key value stores and so on. And yeah, we're obviously around. And the last thing is, the notebooks are growing. This is essentially an attempt of writing a book in a collaborative open source manner. In other words, if you feel compelled to write a notebook, send us a pull request, or if you find something that needs to be improved, send us a pull request and we'll incorporate it. So this way, this can go much faster than a traditional book. There was a question in the back. Okay, the slides will be available on gluon.mxnet.io. So gluon.mxnet.io, you'll find the slides there. There'll be a link within the next 24 hours. There will also be a discussion board there where you can then discuss the slides and notebooks and other things, and ask Gluon-related questions. Okay, so see you again after lunch.